couple of things. So I received some information about a program that is going to be started at Fresno State. It's like sort of a pre-med program, but the idea is to get students that are going from, let's say, community college to Fresno State to UCSF for med school. And so anybody interested in med school? So you guys would be interested in this flyer, right? So let me print out the flyer. I will have Mauricio, I'll print out a couple copies. Only one person ready to go to med school? Anybody thinking about going to med school? Okay, got 3. Okay. Door unlocked. You gotta pick that for me. There's also a handout. And not in my office. Yeah. So take your time, because it'll take a minute. And I just got word about a engineering conference at San Jose State that will be happening for those who are planning to go into engineering. It would be a great opportunity to network. So I will also get that information printed out. Look it up. Yeah. Yeah. Oh, okay. But it won't be up here. Oh, that's the one. So, did anybody do anything fun? No? You guys are so excited. You act like it's a Monday or something. Monday? Did you do anything fun? I was actually here on Monday. I was working. I did a lot of homework. So somebody else was working too. Working all day today. It's fitting, right? Let's see. So, take chapter 1, right?
Yes.
Okay. We're ready to start chapter 2? Yes.
It's good.
Okay. So, some of the early ideas about the atom. Well, a long time ago, the Greeks used to believe, well, first off, they came up with the word atom. Atomos basically is where we get the word atom. It means indivisible, so it's not able to be broken down. We're not able to break it up into little pieces. They also kind of believe that the elements were composed of fire, earth, air, and water. And so those were the 4 elements that they believe that made up your body, and that's what you were. Or you can be 2 of the, two of the elements, or one of the elements that you are, right? And so for a long time, people were just trying to get an idea of what makes us what we are, what were the elements. And so Dalton comes along, and Dalton proposed his atomic theory. Now, Dalton's atomic theory consists of 5 parts. Okay, matter is composed of small particles called atoms, and then the atom is the smallest unit of the element that can participate in change. And I guess you don't have a copy of these notes. Okay, so let me print out a copy of the notes for that. Thank you. It's got a cross check. $550. I'm keeping your tab though, just so you know. Oh my gosh, it's like I had a copy. I believe somebody else should also not have a copy of these notes as well. So then you probably have this. And you have a copy of chapter 2? Okay. So, where was I? Okay, so we know that the atom is supposed to be the smallest unit, right? And it can't be broken down anymore. So that was one of the first things that Dalton said. The atom is it. That's all it is. It can't be divided, it can't be cut up or anything like that. Now, an element consists of one type of atom, right? And so we can kind of agree with that because we kind of define what an element is. An element is going to be consisting of one type of atom. So in our cases, we can have a diatomic element, a polyatomic element. We talked about those already, right? You guys remember the diatomic elements? Yeah. Right.
Oh, nice.
Oh, you're doing one of those? Yeah. Give me one of them. Give me one. Oh. Diatomic. Okay. Exactly. Okay. Oxygen wood. So we got oxygen and we got wood. Nope, helium is not. Now you're just guessing. I don't want you to guess it. You should know that. You guys don't remember the diatomic element we talked about last week after school? Yes.
Okay.
Yeah, it is a have no fear. So I'm not going crazy. I did talk to you guys about this. Have no fear by cold beer. So tell me. So he said oxygen is one of them. So that one. Nitrogen. Okay, that's 2. Fluorine. That's 3.
Hydrogen.
Hydrogen. That's 4. And you said iodine. That's 5. Bromine. That's 6. There's one more. Was it?
Argon.
No, not argon. Argon is a noble gas. You should know this. Chlorine, right? So if you guys remember, it's that 7 in the corner, right? You have nitrogen, oxygen, fluorine, bromine, iodine. I can actually visualize it. Visualize the periodic table. You guys have a periodic table on the tape, don't you have that 7? I mean 6 in the corner, and then plus hydrogen. Okay, so another way of remembering is have no fear of ice cold beer, right? Another way of remembering it. Yeah, but you knew this, but you're not using it. Come on now. Don't throw the stuff, because you can't throw the stuff that we're learning out the window. You got to keep it up here, right? Otherwise, you guys are gonna be in a lot of trouble. Okay, now back to Dalton. So Dalton basically said he recognized elements going to consist of one atom, right? And so he also said that all atoms of that element are going to be exactly the same, right? So here's an example. Long time ago, pennies used to be made of just copper, right? And so this here represents the ball stick model of just copper, right? So this is just copper alone, right? So in the case of a penny, right? A penny is about 3 times 10 to the 22nd copper atoms. That's going to be made up of a single penny. That was in the 80s, right? Or the 80s, you know? Okay. So then Dalton says that atoms of different elements are going to have different properties. Right? So carbon is going to be carbon, and oxygen is going to be oxygen. They're not going to behave the same way. Okay. And they're going to be different properties that are going to be associated. Okay. So, and then he said that you can take 2 atoms and combine them together, 2 different atoms and combine them together to make a compound. All right. So, and that compound is going to be existing in a whole number ratio. So, for instance, for carbon dioxide, I have 1 carbon and 2 oxygens. Right. So it's a 1-to-2 ratio. For carbon monoxide, I have 1 carbon, 1 oxygen. It's a 1-to-1 ratio. But it's always going to be a whole number ratio. Okay. And then the last thing he says, and this is that whole part about being indivisible, is that atoms can't be created, destroyed. They can only be changed, right? They can change parts in a chemical reaction. Okay, so they can be rearranged in a chemical reaction to make a different type of metal. Okay, and so we've already talked about it that in terms of the chemical equation. This last one kind of deals with the law of conservation, right? So now that you guys know that Dalton's atomic theory, are they all true? No. Which one is it and why? I got 5 choices.
No. I know.
Anybody want to help out? Yes.
Atoms are not the smallest particle.
Okay, so that's one thing that isn't true. So atoms is not the smallest particle. So what can atoms be broken up into?
Protons, neutrons, and electrons.
Subatomic particles, which are protons, neutrons, and electrons. And now that we know that we can actually break up protons, neutrons, and electrons to even smaller particles, right? So, which I had planned to give a whole nother lecture on, but I didn't get a chance to pull it together. So you guys gotta wait for that. So when we really get into the next level, we'll talk about that. So that's one. Is there anything else?
An element is consistent of only one set of atoms.
Okay, so you disagree with that?
Yeah.
Okay, what's an example? Why?
Phosphorus.
So what?
Phosphorus has more than sulfur. I think I'm misunderstanding.
You know, I think there's he's saying that when we talk about an element, you only have one type. You only have phosphorus.
Oh, I see.
Yeah. But what you're saying is there's something else that kind of deals with that. Anybody want to help them out? Any other thing that you guys can think of? That's right if you can't, that's what you're here to learn. Yes.
I don't know if this counts, but number 5, atoms cannot be created or destroyed. They
Okay.
can also be technically transformed into other atoms
Okay. How?
through nuclear fusion and fission.
Okay, so that's another one that is incorrect in a sense. Yeah. So that's good. One more. There's one more, the one that he was sort of, running around a little bit.
Yeah. So
So are all atoms of a given element exactly the same? Say no. Why?
Atoms have different types called ions, which are atoms have different numbers of electrons.
Okay. So yeah, that's sort of right, but there's something more major about that, other than the ion, which we will be talking about today. So that does deal with it a little bit, yes.
that was it. Sorry.
That's all you got? Anyone else? Have you heard of isotopes?
Yes.
Isotopes. So, for instance, there is carbon. Carbon exists in two forms of isotopes, two major forms, so technically three, right? So there's carbon. You mind if I use the board? If I let everybody see the board? Hey, guys, you guys just stop yelling at me. You guys are just talking way too much.
Wait, wouldn't radiocarbon dating be one of those isotopes?
Oh, I didn't say that an hour ago. You said this an hour ago. You're just saving up.
And then also uranium as well.
Well, that deals with the nuclear, right?
Yeah.
So. Okay, so this number here is called the mass number. This here is called the atomic number. And then occasionally you'll have a charge that will be associated over here. So this is going to be our ionic charge. So we'll talk about that. Although there's nothing here, this just represents the surface. Okay, so that there is going to represent where the ionic charge is going. All right. Okay, so these guys are considered isotopes of each other. So in nature, these isotopes exist. The most abundant one is 12. That mass number is also associated with the weight or the mass of that isotope. So this carbon here is going to weigh 12. If you look on your periodic table, everybody has their periodic table available? Yes, no, maybe? Switch over to my periodic table. Okay, on your periodic table, this number here, that represents our atomic number at the top. This number here represents the mass. So if we take a look at carbon, take a look at carbon. Carbon has an atomic number of 6. Now, the atomic number defines what the element is. The atomic number of an element is never going to change. It also happens to be the same number as the number of protons in the element. Protons are positively charged. Okay, so carbon has 6 protons. And we'll talk more about this here in a minute, but I just want to kind of talk about it a little bit. This here represents the atomic mass. So this is the atomic mass that we have on the periodic table. The atomic mass that we have on the periodic table takes into account all of the different isotopes that we have. Carbon has 3 isotopes. It has carbon 12, carbon 13, and carbon 14. Carbon 12 weighs 12, carbon 13 weighs 13, and carbon 14 weighs 14. Okay. Now, carbon 14, we have what we call trace amounts. You know what I mean by trace amounts?
What's left over?
No, trace amounts, the word trace, what's that mean? It's trace. You have trace amounts of something. You have trace amounts of what was that? Copies? No, so when we make the reference to that term trace amounts, it means that we have very, 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 very little that we don't really account for, right? Because it's so little we can't account for. So it's trace amounts. So you may have trace amounts of lead in your body right now. It's not going to kill you because it's trace amounts, right? So when that term trace means very little, right? Very, very little amounts. Yes.
Is it kind of similar how bodies have trace amounts or not?
Exactly. Nitrogen we have quite a bit, not trace amounts. Quite a bit of nitrogen. But yes, so that is very similar to that. Okay. So this guy is going to be negligible in a sense, right? Because they're doing so little that we're not going to take into consideration. So we have primarily carbon 12 and carbon 13. Okay. Now, if you look at it, it takes the average of all of the carbon that we have available. Look at this number, it's 12.011. It's an average of all of the carbons that we have. So it's closer to 12, much, much closer to 12. So we're going to assume that carbon 12 is going to be upper 90s, right? It's going to be like 99.8, you know? So, and actually, if I remember correctly, I'm just going to off the top of my head, we'll look at the numbers on my slides here in a second. It's like 99.89%. And then this guy is like 1%, right? So it's like 0.11% of carbon 13. So the majority of the carbon is carbon 12, right? So meaning that it weighs 12. So there's a distinction between carbon 12 and carbon 13, even though it has the same number of protons. Okay, the number of protons for both of them are exactly the same. Okay, so that's an example of an isotope. Now, carbon 13 is used for carbon dating, right? You guys heard of carbon dating? Okay. Okay, so let me just tell you, let me get this off your mind. I know you're thinking it. It's not carbon calling everybody up. Hey girl, are you free? You want to go out for dinner? No, it's not that, right? Carbon dating is actually using carbon 13 to determine how old you are, right? Or how old something's been around. Because carbon is so little, there's so little of it around. There's in nature, there's 0.11%. That is very, very little, right? So the longer you've been around, the more carbon 13 you're going to have in your body, right? So for instance, Juan here has probably been around probably 19, 18. He's been extra 18, right? So he's probably has very, very, very little carbon 12. Where I know that he just had a birthday for 23 now. He's 23, so he's going to have more carbon 13 than Juan does. So by looking at how much carbon 13 he has in his body and how much he has in his body, I can get an idea of how old they are, right? So we can do this with very, very old things because carbon decay, carbon 13 decay, happens very, 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 very slow. So the oldest thing on Earth, we can sit there and use that to tell how old it's been, how long it's been around on the Earth. And that's what they use to sit there and determine how old fossils have been around, right? Or how old trees have been around, or how old I've been around, right? I've been around a lot longer than he has, just a little bit longer than he has, right? You know, I'm 21 still, you guys know that, right? So So anyway, we can use that to sit there and help us age things, because we know that one thing, carbon stays around for a long time, and not only that, there's very little of that. So the more of that you have in your body, the older you typically are going to be. Okay. So let's get back to the talk here.
You don't pass out the paper.
Yeah, that's not
That one is broken.
so considerate.
In this chapter 5 or just for Chem 2?
That's for Chem. The only print that many copies of it?
Yeah.
So leave it there. That's for, that's not. Okay, so. And we'll get back to this. We haven't got too far, and we'll get more back to the periodic table. So don't worry, you haven't missed it. Okay, so remember when I talked to you about that whole thing with ratios? This is an example of that, right? So we have copper 2 oxide. Copper 2 oxide is a combination of copper and oxygen that are coming together. So initially we started off with just copper and oxygen. We put them in a jar together, and then they end up making copper 2 oxide. Okay, so this is what this is just showing you here. The copper, there's the oxygen, and then as a result of that, we get copper 2 oxide. Yeah. Okay, so that tells us that we can go with those elements, and those elements can combine or go through a combination reaction, or what we call a synthesis reaction. Only for 15 minutes. So it was only people that were interested in becoming doctors. Oh, anybody who's not interested in becoming doctors, don't worry about it. I got something else for you.
I think it's more stuff.
Yeah. Okay. Okay. So was there anybody else interested in becoming a doctor over here? Are you sure? Okay, I'm just saying. Some opportunity. Okay. So that brings us to the law of conservation. We've talked about the law of conservation. Do you remember the law of conservation? Let me pick on somebody else. Do you remember the law of conservation? Okay, help me out. Preach, bro, preach. Church that.
Yeah, it's probably best to each someone else.
No, I want to hear from you. It's okay. Law of conservation.
Yeah, I can't remember.
Come on. Give it a time. It's breaking my heart here. I know you know it. You know something. Just tell me anything you can think of. Conservation. What do you think that means?
Matter can think of a different word, but I'm trying to remember the words that I think it'd be broken down, but it can't be lost.
Okay, so you're saying that matter can't be created or destroyed. It can only be changed, right?
Yeah.
Okay, so that's what it boils down to. At the end of the day, matter can't be created or destroyed. Meaning that you can't just all of a sudden make something happen right here, right? I can't make a beautiful woman right here just by thinking about it, right? Does that happen? No. It hasn't happened yet. I've been thinking about it for a long time. It still hasn't happened, right? So it's not just going to happen out of the air. So what's going to happen is that there has to be some type of change that occurs, some type of chemical change that happens. And at the end of the day, what I put in that initially is what I'm going to get out. The only thing that's going to be different is how it's going to be rearranged. That's the only thing that's going to be different. So what I put in is what I get out. Okay. Now that's going to happen whether you have a nuclear reaction or you have a chemical reaction, right? So everybody says, oh, chemical reaction breaks the law of that. Actually, it really doesn't, right? We account for it, but we account for it differently. And we'll talk about that a little bit later. Okay, so the law of definite proportions. The law of definite proportions basically says, and I'll break it down, is that if I have two elements, in this case, we have hydrogen and carbon we're using a compound called isooctane. Isooctane is going to be C8H. I think it's going to be C18. Yeah, C18, H19. Okay, so isooctane, sorry, actually no, 18. C18, H18. Okay, so if we actually look at the mass of this, the ratio between the mass of the carbon and the hydrogen, it's going to be a 5.33 to 1 ratio. So 5.33 to 1 ratio. So if I have, let's say for instance, if I have 5 grams of isooctane, right? The ratio is always going to be, look, don't worry about it. Just relax, don't get worked up. It's nothing to get worked up about. So we have a 5.33 amount of carbon, that mass of carbon, to 1 gram of hydrogen. Okay. Now, if I have a ton of that, right, that ratio is going to be the same because we have exactly the same element. Sorry, exactly the same compound. Not element. Exactly the same compound. Yes.
Let's see what you wrote.
Oh. I wrote basically this right here. So that ratio. That's all I wrote up there. So I have 5.33 grams of carbon and 1.00 grams of hydrogen. So if I take the weight based upon how much it weighs, it's always going to be that ratio. Because I know, oh, you probably didn't see this part. See, I write it over here, C18, C8, H18. Okay, so if we take the weight of this by using our periodic table, can you guys do that for me? We'll just do it. Kicks and giggles. So the weight of carbon is what? I can't hear you.
12.0.
Okay, so we're gonna say just estimated to be about 12. So 12 times 8. 96. Okay, 96. And then hydrogen, how much does hydrogen weigh? 1. So hydrogen is 1. So 1 times 18. Okay, so if we divide 96 by 18. With the calculator. Is it humid in here or is it just me? I know I'm usually just hot anyway, I'm just hot, you know, but
5.3.
what was that?
5.333.
So it's 5.33333. Okay, so for every 1 hydrogen, I have 5.33 grams of carbon. Okay, so exactly what I just told you here, right? So that's just proving. Okay, so that means that regardless of how much I have, that ratio is always going to be the same because the ratio, that whole number ratio between carbon and hydrogen, for every 8 carbons, I have 18 hydrogens, right? Because that's the ratio that we have. So for every 8 carbons, I have 18 hydrogens. So anytime that I'm working with isooctane, it's always going to have the same chemical formula. I'm always going to have the same ratio. So its mass ratio with each other is going to be exactly the same. Whether I have 5 grams or I have 5 tons, that ratio is going to be exactly the same. So it's not really saying anything, you know, extravagant. It's like, ooh, right? It's just math. It's just simple math. It's just the ratio is going to be the same whether you have a little bit or whether you have a lot. That just basically tells us that isooctane is always going to have that same chemical formula. It's never going to be different than that. That's all it says. Right? So it's not like groundbreaking news, although they thought it was groundbreaking news before because, you know, they used to think that you could sit there and get gold from anything, right? You get gold from pea, right? Pea in a pot. Oh, I can get gold from this, right? They thought you could get gold from anything. So it was groundbreaking at that point because it just basically showed that you can't get something not by not doing anything to it, right? You can't just look at something and all of a sudden, okay, now I have gold. I looked at it, right? It doesn't work that way. If it did, I'd be rich. I think about gold and beautiful women all the time, and I don't have a beautiful woman here and I don't have any gold to spend it, Oh, yeah, all right. So, okay, are you guys good right now? Understanding? Okay. So, now this also works because sometimes we get in situations where we have two elements that are in a compound, but they're different quantities. Like for instance, we could either have, I'm gonna write it over here so you guys can see it. Tell me if you guys can't see it, because I'll put it on the screen so you guys will be able to see it. We have Cu, Cl, and we have Cu, Cl2. Okay, now these are two different compounds. What is the difference between them? Can you see it?
Yeah. How many COs we have?
How many Cls we have, right? Because in one compound, we have a 1-to-1 ratio, right? In another compound, we have a 1-to-2 ratio, right? So that's what we're kind of seeing here, right? So one compound, it's green, right? The other compound, it's brown, but it still has both the same elements. It's just the quantity of the elements are different. Here, this guy is, it's 2-to-1, right? A 2-to-1 ratio. This guy is basically a 1-to-1, roughly, right? A 1-to-1 ratio. Okay. So let me show you. Okay. So in the green one, we have a chlorine, right? And so we have alternating between chlorine, copper, chlorine, copper, chlorine, copper, chlorine, right? Over here, for every one copper, we have 2 chlorines attached. For every one copper, we have 2 chlorines attached. For every one copper, we have 2 chlorines attached. Okay, so this one is that 1 copper to 2 chlorine. This is that 1-to-1 ratio, right? And so the difference that we see is we see a color difference, right? Isn't that physical properties? Right?
Yes.
So they have different physical properties. So they're gonna have different chemical properties, right? They're not gonna behave exactly the same way. You guys understand that? I'm saying what you can see, right? So you guys kind of see that? Okay. And so that's going to be important for us to understand. So we know that things, even though they have the same elements in them, right? They can behave differently. Like for instance, you guys eat sugar?
Yeah.
You guys eat vinegar?
No.
No? Nobody eats vinegar? You eat
Apple cider
pickles?
vinegar?
You eat pickles?
Oh, yeah.
Oh, so you do eat vinegar, right?
Yeah.
So we know that vinegar, which is acetic acid, is also in pickles, right? We often use that, right? But do vinegar and sugar taste the same?
No.
Everybody's home, exactly, right? I can exchange them, right? I can have, put vinegar in my coffee.
I want to.
I know I can, but nobody says, it ain't gonna taste good, right? So nobody does that. Nobody puts vinegar in their coffee, do they? Right? They have exactly the same elements in them. Vinegar is composed of carbon, oxygen, and hydrogen, right? Vinegar has C, H, and O. We already talked about glucose, right? Glucose also has CH and O, right? But regardless of that, whether they have CH and O, it's that chemical formula, right? We know that sugar or glucose is C6H12O6, right? And then vinegar, let's see if I can remember it, it's HC2 3O6. Okay, so okay, quite different from each other chemically, right? So, but they have that C and a H and O. Just because they have CH and O doesn't mean that they're going to behave exactly the same way. They're not going to have the same flavor. They're going to have different physical properties. Okay, is with me so far?
Yes.
Okay, so we already talked about the atom. Let's break it down. you told me that there's protons, neutrons, and electrons. I'll put it, let me turn on the board here. And we'll talk about everything that Dalton said, because you guys are already ahead of the game. So Dalton says that things could be broken down. You guys already told me that that wasn't true. We can break it down to protons, neutrons, and electrons. So atoms are composed of protons. Now, protons are positively charged. They're composed of electrons. Electrons are negatively charged. And they're composed of neutrons. Neutrons are neutral charge. They have no charge associated. Okay. Now, if we go to the periodic table, you guys all have your periodic table available. I was talking to you guys about the atomic number. Did everybody get that down? Or I switch it over? Okay, so you guys look at your periodic table, running everywhere. And up here, that's going to be our atomic number. That tells us the number of protons that we have for this particular element. So fermium has 100 protons. It has 100 protons. Okay. Now, every element or every atom on the periodic table is neutrally charged. What do I mean by that? What do I mean by that?
I mean, there is no charge.
There is no charge. But I just told you that it had 100 protons, which is what charge? Positive. So I have 100 positive charge. So then how many negative charges must I have?
100.
I have to have 100 for it to be neutral. So we know that electrons are negatively charged. So that means that we have 100 electrons. Okay, now the next part is neutrons. So this here represents the atomic mass, right? And the mass is going to be composed of the number of protons plus the number of neutrons. So if I know that the number of protons, can I calculate the number of neutrons? If I have the mass? Okay, so I can do that, right? So we can take that mass number. What is the mass number for this guy? 257. And then I subtract the number of protons, 100. And then that's going to give me my number of neutrons. So 157?
Yeah.
Sure, my work over here.
Dr. Henry, what units is that in?
There's mass number. We're going to say AMU, atomic mass units. And we'll talk more about that here in a second. And then it'll all start making sense when it all comes together. So, but its mass number is typically it's just given the number because you use the number to get what you want. So it's no units. This is a question. Okay, so you guys see that, right? Okay, so then we're able to sit there and determine the number of neutrons that we have. Now, there's a lot of history with how they figured this all out. And we're going to talk about it very, very briefly, so you guys get some of that history, and some of that insight. And then we'll also start talking about what that AMU stands for. Right? Okay, so but before we do that, I want you guys to test this out. Okay, so let's say instead of fermium, we had carbon. Keep it small and simple, right? We like carbon so much. So now we're looking at carbon. Okay, so what is the number of protons that carbon has? How many electrons does carbon have?
6.
And how many neutrons does carbon have?
6.
6, right? Because again, in that case, it's 12.011 is the number that you have on your periodic table. You round it to the nearest whole number, and then you subtract the number of protons, right? So we have, its mass number is going to be 12. 12 minus 6 is going to equal 6. Okay. Yes. Got that? Yeah. Did I say it too fast? Okay, so you guys ready for another? You guys, you guys got this. This is your wheelhouse, right?
Yeah.
So let's do something fun. Let's do bismuth. I think you got to find out what it is. What's the symbol for bismuth? Bismuth.
Bi.
Bi. Okay, so we're looking at Bi. Can you tell me where Bi is located at? Oh, let's see. Alyssa. Tell me the period and the group. Okay. Found it? Okay, so what group is it and what period is it? So group is the numbers at the top, and then period. So it's group numbers at the top. Number at the top. So group where these numbers are top. 15. Okay, 15, and what period? Okay, so we're looking at 6 and group 15. So what is the atomic number for bismuth?
83.
83. So that means what?
83 protons and electrons.
So there's 83 protons and 83 electrons. Okay, how many neutrons? Said 126. And how did you get 126? Okay, so we had 209 minus 83, and that gives us 126.
Yeah. The mass is of 208.98, so you would round up to 209, right?
209, yeah, and then you said 83. Okay. Oh, yes, yeah. Okay, questions? Good job. Any questions, concerns? Cash? Good. Okay, so move on. Don't worry, you get more opportunities to show those skills. Crap, I have a meeting. So what we're gonna do is, I'm gonna give you guys a couple of things. I'm to deal with my COVID issue. So I'm gonna give you guys an opportunity to deal with a couple of items. And so you guys can talk about it. And then I'm gonna have Mauricio introduce cations and anions. Okay? So, whiteboard. So, we'll give you guys a couple of them. Let's do lithium. And actually, I want you to do hydrogen. So I want you to tell me the number of electrons, neutrons, and protons for hydrogen, lithium, and let's do platinum. Okay, and I'm gonna go to my meeting real quick. I had to take my computer. So after they're done with that. Yeah.
Platinum. I said wrong. I said wrong. It's not. Platinum.
78, 78, and then 117 for the neutrons.
117.
117.
Did everyone get 0 for?
Yeah. I wanted to.
That's not gotta verify, right?
Is that the only one that's 0 on the chart, if you know?
Yeah, for electrons.
Why did I have to?
What makes it special, you know, what they have in 0?
Let's pull that one.
Yeah, forgot the reason why it doesn't have a neutron. I'll bring it up to Dr. Henry because there's a reason behind it. Just can't remember right now.
Cool.
They're making it in there.
That's the question too.
You're not sure. So everybody get this at time.
Yeah.
Oh, you got one over there.
Anybody have questions?
How many think $1 million? Bring it up, so.
Related to.
Don't put the-
Has anybody heard of cations and anions? Just your.
Yeah.
Thank you guys. Has anybody heard of them?
Just right.
What do you think it's related
The kind of charge it has?
to? Anion. It's also ion. So a good way to remember it is the T less or the entirety of pet.
Oh, I see.
Different types of things, and then anion is a negative ion. You think of it as one.
Or double negative? Those two ends?
That's another way. How do you think ions come about? What changes?
For electrons?
Guys,
Maybe.
so it's always the number of electrons that change. It's either taking more electrons in or it's giving them away.
So the number of protons and neutrons are constant unless it's unless it's isotopes. Yeah, 31 over there, something.
You do the joke?
Yes. Yeah. No reactions.
Of course, they're so like today, it's like a Monday or something.
Yeah, one of these two used, can they be like work together when it comes to their charge or?
Like your question.
Appreciate that.
What's a good example?
But here's creative taking. What's creative taking? Yeah.
Nothing I forgot to mention. The charge is straight. Top right. For the other elements,
And oh, you want to give them another?
yeah.
Let's do over tonight.
So basically, to answer your question. 2 plus and so on. They usually add up together to visualize and they form. Ions in general. So there's different ways it doesn't. There's groups, there's nitrates. You guys have it in your
We haven't talked about polyatomic. We're getting there. We're getting there.
get into it.
Yeah, you're getting a little too ahead. Let's talk about this. So we're through it. So no, so you've got way too ahead. Let's just talk about it from individual, right? Let's talk about TA plus 2, and then talk about sulfur minus 2. Get ahead of the game. So that.
You want me to talk about the metals?
Just talk about charts because they can understand. So help them go through another one, right? So we're talking about TA. So we have TA 2, right? So we told you that you're starting out with the number that you initially had for TA. So what would be TA? So where's TA on the periodic table? Okay. what is that? So there's 20 is it helps us tell me what period and what group. Group 5, period 6. Okay, everybody sees it? What is its atomic number?
73.
Okay, so write down the atomic number. Oh, that's not really right. Right. Sorry.
Why do you write the atomic number at the bottom of the periodic tables on top?
So this is actually how we would write the nuclear symbol. So it lets us know all the stuff that we need to know about the nucleus and all that. Because you have, it's just tradition, right? So this here is where you're always going to put your atomic number. Right? So that will let us know what that atom is supposed to be, right? This up here is going to be what we put our atomic mass. So it's going to be the mass, what we call the mass number. Okay, so we're going to use what we have on the periodic table. So then we're going to round that out to about 181. Okay. So that will be the mass that's associated with that. Okay. Now, again, what you see on the periodic table is an isotope. It's a combination of all the isotopes added together that occurs naturally in nucleus, right? And so what you see 181, 180, and 181 added all together. So that's what we see on the periodic table. But if we're talking about one in particular, we would just use that one. We wouldn't use that average. Okay, because we're just talking about everything in nature, we use the average. Okay? If you don't know which one you're getting, you're going to build up all this, right?
Unless we know exactly which one.
Exactly. Okay, so atomic number. Atomic number means what?
The protons and electrons.
Number of protons. And you said number of electrons, right? That's going to change now, right? Because we are 2 plus. Since we're 2 plus, that means we lost 2 electrons. Okay, so now how many electrons do I have?
Be 71.
Right. Straight to right. He's like, I'm never doing this, right? Okay, so the charge helps us. If it's a negative charge, that means we're gaining electrons, right? And that makes sense because you're starting at 0, right? So if you're gaining electrons, it's going to cause it to be negative. And then if it's positive, that means we're losing electrons. Okay, because again, we're starting at 0, we're losing electrons, so that means that overall we have more protons than we have electrons, so we have a positive charge. Okay, now how would I calculate the number of neutrons?
Check the mass of the protons.
Subtract the mass from the number of protons. Okay, so the mass was 181. 181 minus 73.
107.
108. Okay. So does that make sense about the ions? Okay, so yes.
So, like the test, for example, we want us to always put this up right at the bottom.
Yes, the atomic number would go up. Yes, so the nuclear symbol, so normally when you're just writing this and writing this up like this isotope, the very top number, right? This number up here is always going to be the weight, right? Or its mass number, right? The number here is going to be the atomic number. That, the number here with the charge associated with it, that's going to be our ionic. Right? It lets us know its charge or ionic charge. Okay, so and that's the way it's always going to be written. Okay, so when we're talking about isotopes or we're talking about nuclear reactions, right? You guys got that? Okay, so now he was getting way ahead of himself, right? Because we haven't talked about how these guys are going to come together. You know, that's a chemical reaction. Did I get it? Where you at? But I want you guys to do the same thing for sulfur. Okay. And if you don't have, like sometimes you'll just see the TA by itself, TA 2+, right? So that means that everything is normal, right? Except for the number of electrons, right? So you don't have to worry about it. So it's also written that way too. So now get your ion, so you can give them the important food sulfur. And I really still got lucky because, last semester I had, how many I think I had 5 students and I had 4 TAs, and so everybody had their own TA. He would always let somebody else get on the board, so now he has to look up those skills. You don't do it, you have to do it. That's okay. And I'm okay.
What's the number? 16?
16. 18. 16. 16.
Okay, piece of cake? Yes.
You get the number in the charge.
Excuse me?
How do you get the ionic charge?
Ionic charge?
Yeah.
Okay, so we're gonna work up to how you would get it. So right now it's being given to you, right?
Okay.
We haven't got to the point of how you would figure out on your own. Don't worry about it, we will. We're building up to it, right? So it's a process. Okay, you guys are good? You guys feel comfortable?
I had one question. So, since minus, why wouldn't we lose photons to gain electrons, or does it stay the same?
No, the number of photons always is that.
So it would always stay the same.
Yes, only the number of electrons.
The changes. Okay, that was no.
I want to remind you again, the number of protons define what element of the charge. That is never going to change. Yes, yes.
I have a question that I tried to ask him earlier.
Uh-huh.
Why is hydrogen neutron 0?
So let's do hydrogen. Put it up there. This is fun. Did he just give you the answer? How you got there?
No.
I asked him for that.
Oh, but then you didn't explain it to the whole class. You gotta explain. You can't just put answers up there. You gotta explain them. Yes, you have a question.
Yeah, so like the positive charge, I'm trying to like, put it, like, so since it's positive and we're subtracting, it's just like charges repelled.
Yeah, because so normally we have positive and negative, right?
Yeah.
Positive and negative, they come together, they neutralize each other.
Yeah,
Right.
okay.
And so since they're neutralizing each other, so if we're getting rid of 2 positive, right, that means that we have, we're getting rid of 2 negative, that means that we have 2 positive that are just there alone, right? And so then that way you're getting that 2 positive charge.
Right. And then add the negative charge.
That's right.
Okay.
Oh, don't worry about it. We're gonna add a whole nother layer to that. It gets pretty cool because you start thinking about how is it gonna behave. You guys need to know a little bit more before we get there. Okay, so we're talking about you gave all of the answers and everything. So you have how many protons for hydrogen?
1.
1. Okay, so we know that we have 1 proton, right? How many electrons do we have? 1. How much does it weigh?
1.
1. Okay, so if it weighs 1, right, and we have 1 minus 1, what does that equal?
0.
0. So then how many neutrons will we have?
Zero.
We're gonna have 0. So does that make sense now?
But you want to explain why and
What?
why is it so specific? Because you also mentioned that was the only one that has 0 neutrons.
Yeah, it is, because it just works out that way mathematically, and then also because, well, if you look at hydrogen, in all honesty, there are 3 isotopes of hydrogen. There's hydrogen 1, there's hydrogen 2, and there's hydrogen 3. That's the way we describe the different isotopes. We just say they're weight, okay? Hydrogen 1 weighs 1, hydrogen 2 weighs 2, and then hydrogen 3 weighs 3. Now, the difference between hydrogen 1 and hydrogen 2 is what?
Atomic number?
No, it's not. It's atomic number. It's hydrogen. Its atomic number is always going to be the same. It's going to have an atomic number of 1, right?
Different number of neutrons, right?
So it has a different number of neutrons, right? Because the weight is changing because of the neutrons, right? And so the thing is that hydrogen, for its stability, it likes not to have a neutron, right? So it doesn't need that neutron to be stable. So it's not going to use it, right? Where the isotope of hydrogen, which is hydrogen 2, right? Hydrogen 1 and hydrogen 2, that isotope, it needs that neutron for its stability or somewhat stability. And it's not too stable, actually. It actually decays pretty fast compared to hydrogen 1, right? Which is the normal one that we see, the most abundant. Okay. Yes.
Oh, no, I was just searching.
Okay. Yes,
Can you give me a clarification about isotopes?
sure. So isotopes. So let's just kind of break it down. Iso means the same, right? So an isotope is the same atom, but different atomic mass. Okay, so my examples were, just a second ago, was hydrogen 1, okay? And hydrogen 2. Okay, so those are examples of isotopes. Hydrogen 1 weighs 1. Hydrogen 2 weighs 2. Right? They're different from each other because they weigh different. But they're the same atom, they're both hydrogen. Okay? They're incorporated the same way. So if we're making a reaction, they're going to be incorporated the same way. So they're just going to weigh different. Yeah.
Questions? Yes. Do you need different isotopes to be able to formulate different compounds?
Yeah. So again, it's the same atom. It's going to behave just like that atom does. Okay. It's going to have a lot of the same properties. The only thing that's going to be different is
Neutrons.
the number of neutrons. It's going to weigh different. That's it. Okay. And then also, there's one other thing. Sometimes it's stability. Sometimes certain isotopes are less stable. So typically when you have one that is, like for instance, we talked about carbon 12 and carbon 13, right? Carbon 12 is very, 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 very stable, right? So that's why we have so much of it, right? Compared to that. That's why we have 99.85% in nature. Compared to carbon 13, which is 11%, because it's less stable than carbon 12. Right? So the one that's the most stable is going to be around the longest. Yes. Okay. No, did you just answer? Think about what we asked. Think about the question. Said, would its stability be a factor in how well it decays, right? So if you think about what you just said, right? Stability, when you say decay, you said it's unstable, right? So in stability and decay should go hand in hand. So your question is, so you think, rephrase your question, because I think I understand what you're trying to ask me, but I want to be clear. So think about your question. Okay, get back. Thanks for explaining. Okay, so do you guys, does that help you with isotopes?
I had a question. Can you make more carbon 13 from carbon 12?
Yes, we can, right? And then, but that usually means that what are we gonna add to carbon 12? We're gonna add a neutron, right? So technically in the lab, we do that. So not in this lab, we don't have the facility to do it. And it would cause a lot of other issues because, you know, you're impelling a nucleus with a neutron. Things could go wrong, right? We don't want any bad reactions to happen, and that takes energy or it makes energy.
Yeah.
Right? And so both situations we want to be cautious of because that's what nuclear reactors do, right?
Oh.
That's how you get nuclear energy. So we gotta have to be careful with what we do with that, right? So yes, we can, but we gotta be careful with it. Does that answer your question?
Yes.
Good question. Okay, every atom has an isotope. Almost every atom does have an isotope, but it's whether we have trace amounts or it deals with kind of like the concept of stability, right? So in that case, the ones again that are going to be more stable, right? They're going to be very little of the other isotope, right? So almost every isotope has, every element, every atom has an isotope, but sometimes we don't see it because it's not very stable. So we can't recognize it. Does that make sense? Okay. You have a look. Yeah.
Oh, just to clarify, so cations have a positive charge and
That's right. Cations are positive, positive, and ions are
Oh, I didn't get that on the first one.
negative.
Now you see.
It's presentation.
For real.
See, they laughed this time. How much did you pay them? Okay, any other questions? How you guys feeling? Because it's pretty simple, it's not too hard yet. Hey, it isn't gonna get that hard. I mean, really, it isn't. It's gonna actually, everything is gonna start clicking and you're gonna be, oh, I get it, it's game, right? Now, let's talk about this. He introduced ions. Ions play a huge role in chemistry. Okay, now, the thing about chemical reactions, we're not talking about nuclear reactions. Nuclear reactions are gonna be different. Okay, chemical reactions are going to require a couple of things. They're a couple of things that we didn't think about, right? And that's that concept of that ion, right? So for a reaction to occur, you're going to either be gaining electrons, or you're going to be sharing electrons, right? Now, the reason why you want to gain, lose, or share is because at the end of the day, you want to try to be like the noble gases, right? You want to find stability. How many of you guys date crackheads? Anybody? Anybody? Hey, he's like, what? Is this not an odd question for chemistry or something, right? Okay, so I've dated a crackhead. It's not a good thing, right? And so it's totally unstable, right? It is totally unstable. It is like, you know, they want to be up all night, party all night, you know, sleep all, well, no, they didn't want to sleep, period. And then, you know, you're trying to have a normal job and a normal life. They come in and 1 minute when they start coming down on their high, they want to throw stuff at you, threaten to cut you. You know, it's all crazy, right? It's so crazy. There's no stability involved in that, right? Most of us want stability. Why are you taking this class?
I'm trying to get a better job.
Trying to get a better job. So that means you want stability, right? Because you're saying you want to be financially stable. That's what you're telling me, right? Why are you taking this class? To get a better job. Again, stability, right? So most of us are not looking to go out and date crackheads. I was experimenting, right? It was a time in my life. I wanted a little excitement. I learned a lesson, right? Okay, so exactly, living on the edge, literally on the edge. Let me tell you. So we're looking for stability. Now, chemical reactions are trying to do exactly the same thing. The reason that you're going to have a chemical reaction is because you're trying to find stability. One way or another, you're not stable. You're trying to be like the noble gases. The noble gases are stable. They're like the coolest kids everywhere. Let me show you something. I don't think I showed you this. I lose track because, you know, old age and everything. Meetings in the middle of the class, you know. Let's see.
Can't get it now. I can't get it now, but I can get it. Can't get it now. I can't get it now, but I can get it. Walked up the stairs. I can't get it now. Can't get it now, 'cause the fucker's downstairs. I'm going to grill. Fucker's downstairs. I'm going to grill. I can't get it now. Can't get it. I can't get it now, but I can get it. Can't get it now. Gotta get it now, but I can get it. Can't get it now, but I can get it. I walked up to beds. Walked up to beds.
Okay, so there's a lot to take apart there, right? You guys are pretty excited. So one thing that we learned from that is Carmen's a whore, right? Okay, so that's something that you guys want to recognize. Carmen is a little bit of a whore. Carmen wants to sit there and make everybody happy. It likes to be in the middle, right? It's the center of most reactions, right? And so you guys will recognize that. We'll talk more about Carmen being a whore. One thing that I want to stress is that if you notice, she has the noble gases, right? They're chilling there, right? The noble gases are stable. They're the cool kids. Everybody wants to be like them, right? So everybody is thinking, I want to be like the noble gases. So they're gonna rob, they're gonna take, right? They're gonna give, right? Some of them are gonna give things away, trying to be like noble gases, and sometimes you're gonna share. And if you think about the way that we look at life, right? Some of us, we take, some of us are givers, and some of us are sharers, right? You guys have thought about that.
Yeah.
Okay, so the chemicals are going to be just like people. Try to find ways of getting stable, right? Some of us think that, oh, I can't do it myself, so I need a man or I need a woman to sit there. I need a sugar mama to take care of me, right? I've been asking for a sugar mama. She still hasn't showed up. I'm telling you, if I can get a sugar mama that will let me get away with the things that I want to get away with, we would be there, right? I would care, right? But we often will. A lot of us will sit there. I can do it on my own, right? So you're going to be the one that's going to take, so I can get what I want. I want to get what I want, right? Or some of us are the givers, right? Oh, I got a lot, so let me give you a little bit, right? So that you can try to get what you want, right? At the end of the day, you want to try to get to that point of stability, right? We're finding ways to get stable. The elements are going to try to find ways to get stable, right? So if you look at the periodic table, so we have the noble gases located here, right? Everybody want to be like, right? So the noble gases have their outer shell filled, meaning that they have enough electrons that they're happy, everything is cool, they're the Johnsons, they have everything they could possibly think of. They're happy. They don't need to be in reactions. They can be in reactions, but it's not necessary, right? They'll do it just to help you out, but not because they want it. Does that make sense? Okay, so now chlorine, bromine, iodine, and astatine. Now those guys, they're one away from being like a noble gas. They need one electron. So what do you think they're going to be willing to do? Yes.
Well, I was gonna say, can you clarify those rings again? The shells?
The shells, we'll get there. We'll get there. I don't want to get into that yet, but we'll get that, promise. It's going to take, right? It's going to be willing to take, right? So now the thing about taking, you got to think about this. Now, I know none of you guys are thieves or anything like that, but we can think like thieves, right? You can all put yourself in a situation to think like thieves. Now, are you going to take from your neighbor? Or are you gonna take from somebody who lives in another town?
Another time.
Another town, why?
Get away with it.
Because it'll be harder to get caught, right?
Yeah.
Okay, because if you take from your neighbor and you're riding his bike, right? And he's gonna be like, somebody stole my bike, and he sees you riding, he's gonna, you stole my bike, right?
Yeah.
So it's gonna be immediate, right? So you're not gonna take from your neighbor. So here, fluorine, chlorine, bromine, iodine, and astatine, they're not gonna take from their neighbors, right? They're not gonna take from other non-metals, right? They're gonna take from metals, because metals are way over here across town. So they're gonna be like, hey, lithium, I'm stealing his shit. He don't need it anyway. He's rich. I'll take his electron, right? So they'll take from those. But here, you can go to your neighbor and say, hey, dude, you have a really cool ass bike. Let's share it, right? I'll share this with you if you share this with me, right? And so you can kind of convince your neighbor to share because you guys on good terms, stuff like that. So you're going to share with your neighbors, right? So when electrons are being shared, that's called a covalent bond, right? I'll write it on the board because I need to spell it. Just bear with me. I'm not easy. Okay. Put it on the board. One day I want to figure out if they can get picture in picture, I can get half on one side what I'm saying and we can't. We need to figure out how to do it. So you gonna teach me?
Sure.
I should be able to. Okay. Well, I'll take a class with you here in a second, so you can show me how. Once I figure it out, it'll be great. Okay. So we also have what we call ionic bonds, right? Ionic bonds is going to be that taking and giving. Okay, so in the case of an ionic bond, we have the metals.
So can you give your own specific to like other, not neighboring?
Yeah, you can, but typically it's very rare. You'll give to say metals and non-metals, right? So non-metals will be taking, they'll take the electrons, and metals will be giving the electrons. So if you have a metal that's close to you, metals can do that, right? But you have some metals that kind of like they're metals, but occasionally they do crazy things and they act like non-metals, like beryllium is an example of that. And so we'll talk more about that later on, but you'll get these exceptions, right? And so they'll break those rules. Okay.
For the most part, you're going for ones that really want to take from the ones that really want to give.
That's right. Yeah, that's usually how it works out. And so metals and non-metals. So metals are going to be the takers. Metals are going to be the givers, and non-metals are going to be the takers, right? So when they come together, right? Your metal is going to be giving up the electron. So then your metal is going to have a positive charge, right? And then your non-metal is going to be taking the electron. So you saw that Mauricio was getting ahead of the game. We have that Ta 2 plus, and then you can have S 2 minus. So in other words, Ta gave up 2 electrons, and S came along and took the other 2. It took those 2, right? Because if you look where S is at, S is 2 away from being a noble gas. It needs 2 electrons, so it will be stable. So once it gets those 2 electrons, it's like, hell yeah, I'm good to go. I'm like a noble gas. I'm good to go, right? But it also has charge associated. Now it's a positive charge. Now this is how you guys folks up, right? How many of you guys date? General. None of you guys are dating. You're dating. Okay, 1, 2, 3, 4. Okay, so 4 of you guys are dating. How many of you guys are not dating? I just want to know because by the end of the semester, you guys are going to be going through your ups and downs, and you're going to get that dating mode and those tears and everything, and then you'll be like, "That's what Dr. Henry was talking about." I know it was, right? You guys are gonna get there, so you'll understand. But those who are dating, tell me about your partner. Is she just like you?
Yes, for sure.
Really?
Mindset, goals oriented, focused, and likes to eat healthy.
But is she exactly like?
No.
No.
We don't
Okay,
have
so
to
let's put it like this. Who's the good one? Who's the bad one?
I mean, I'm at the sound the good.
You're the good one? Okay, now if we ask her, she probably say just opposite, but we'll go with it. Okay, so she's the bad girl, right? Because, opposites typically attract, right? Everybody knows that, right? You guys have been in those relationships, and I remember when I was in high school, you're like, oh, I met the perfect girl. She's just, oh my gosh, she's a dream, da, 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 da. And then I tell my mom who she is. She's like, Lisa Johnson. Lisa Johnson is her family is, they just do bad things. You can't be dating her. You're not allowed to date her, right? Yeah. Your mom's like that too. My mom was very, very possessive, just controlling in a sense, right? No, you can't date that person. Yes.
I was friends with like someone that had like a bad rap sheet, or their family had one,
Uh-huh.
and my dad tried to like shut it down.
Immediately, right?
Yeah.
Uh-huh. He's like, nope, that is not gonna happen, right? So you can understand, you can relate to it, right? So we've all kind of gone through that at some point or another. Either you're the bad kid, or at points I was the bad kid, and I went through my changes after dating Mrs. Johnson. I became the bad kid. But anyway, but the idea is that opposites attract, right? You want that bad kid because you're that good kid, right? Like, she's the best thing ever, right? And then so those opposites come together. Now that's the same thing that's going to happen here. You have opposites come together. You have a negative charge and a positive charge. They're going to come together, and they have to balance each other out completely, right? If they don't balance each other out completely, they have to get something else to sit there and add on so that they can balance each other out completely, right? And that's usually what happens in relationships. If you guys are not balancing each other out completely, then you're looking somewhere else for it, right? Looking pretty good over there. I don't know, what's your name, So you're looking to make that change, that upgrade, right? So you're always looking for that balance, right? You're trying to get that neutral charge. And you also want to be like the Johnsons, the noble gases, okay? Now that's the goal of chemical reactions. That's the premise of chemical reactions, is that stability, right? Because at the end of the day, it comes down to stability, right? As I told you, I was dabbling with the crackhead and everything like that, right? She was too much for me, right? She had too much charge, right? She had too much negative in her, right? I couldn't handle it, right? She needed like 50 of me to sit there and balance her out, right? She was just way off the chain type of crazy, right? So the thing is that I knew I can handle it, so I had to move on. I had to try to find something that would neutralize, that we balance out completely, right? Still looking for it, still hasn't happened yet. Working on it. My current girlfriend thinks that she might be that one, but we'll see. Right? It has to be. Right? Okay, so these guys have to come together.
We'll see.
And when they come together, they balance each other out. Because this is the first two, that's the minus two. Now, if they're perfect, they're going to balance each other out. If they're not, they need to find a way to do it, right? And so let me give you another example. Let's say we have lithium. Lithium is going to have a plus charge. And then let's say we have sulfur. It's going to have a 2 minus charge. Okay? So that means I'm going to need 2 lithiums to balance it out. Sulfur is too much negative, right? Lithium needs its twin to sit there and keep them in tank, right? So you have Li2 plus when it comes together to neutralize itself. Okay? Because at the end of the day, it has to have a 0 charge associated. And again, this goes with ionic bonds. Ions come together to form a bond, and it's an electrostatic bond, plus and minus. You guys with me? Okay, good. You had a question. Look like you have a question. You don't have a question?
Oh, no, I'm good.
Okay, good.
And that was a ionic bond?
Ionic bond.
Are we done? Coalinga yet?
We haven't really found out. We'll get there. We'll get there. Okay. Questions? You guys are just getting here, going. We're actually gonna have to stop here because you guys have a lab to do, and once you guys say be able to finish it, we're over actually. So let's can you guys mind just taking a 5-minute break, bathroom break? And then stretch your legs, and then we'll come back to your route, and then we can start with the lap. And then finish this up. One of those works out here. Oh, I can really do it.
That's five, right?
I think it says, yeah, left side.
That's all right.
It's from the side. That- yeah. That's pretty good. We did that so far. You guys did the new chapter.
Yes.
Are we skipping 3?
What, it's chapter 3?
Yeah.
No. Did I give you chapter? You have chapter 3. I gave you chapter 4?
Yeah.
Yeah, it's not chapter 2 and chapter 3, or is it?
No, it should have been chapter,
It was
I-
chapter 4.
I gave you chapter 4. I haven't given you chapter 3 yet.
Yeah.
Yeah.
Okay. Okay, let me give you chapter 3. So,
Yeah, we're gonna need it.
yeah, because you don't need 4 yet. You're giving them 3. So.
I thought it was.
What was that? No, that's in 2A. For some reason, I thought we had another chapter.
Yeah. But for now.
No, it was.
Turn so quickly. It was my I didn't want to see anyone.
Should be.
I didn't want anyone to see me in my right.
Yeah, so you-
It's a nice one.
yeah, so you can be going to Zoom and then also- Yeah. Right here, right here, that just shows that. No problem.